Why urban industrial load pockets are the next frontier for grid-edge battery storage. For much of the past decade, utility-scale renewable development expanded outward. Projects moved into deserts, farmland, and wide transmission corridors where land was abundant and interconnection capacity could be secured with relative predictability. That approach made sense when the industry's primary objective was straightforward: build megawatts and decarbonize the grid. In many organized power markets today, the challenge has shifted. The constraint is no longer simply generation, it is deliverability, it is flexibility. It is the ability to provide power precisely where the system is under the most stress. Urban industrial load pockets are emerging as some of the most strategically important and technically complex environments for battery energy storage deployment. The growing importance of urban load pockets. Ports, refinery districts, logistics hubs, manufacturing corridors, and dense data center clusters frequently operate near substation import limits during peak demand. Congestion-driven nodal volatility has become more visible, particularly as electrification accelerates and computing load tied to artificial intelligence expands. While remote renewable generation strengthens the overall resource mix, it does not always resolve localized bottlenecks. When the constraint is geographic and electrical rather than systemic, location becomes decisive. Strategically sited storage within industrial zones can respond directly to those reliability and congestion pressures. Industrial sites present unique development challenges. Developing battery storage in these environments, however, bears little resemblance to building on rural greenfield land. Industrial parcels are rarely blank canvases. They often include legacy foundations, buried utilities, rail setbacks, environmental overlays, zoning buffers, and irregular boundaries. Civil design becomes a coordinated exercise across engineering disciplines, balancing fire access, crane maneuverability, drainage design, setbacks, and equipment spacing within tight footprints. Early geotechnical investigation is essential, as prior industrial use may influence soil-bearing capacity, contamination management strategies, and foundation assumptions. Interconnection and safety requirements add complexity. Interconnection complexity increases materially in dense load pockets. Substations serving industrial corridors frequently operate with higher fault duty and constrained breaker headroom relative to rural nodes. Storage introduces bidirectional power flow, altering protection coordination dynamics compared to solar-only installations. Relay settings, inverter response characteristics, short-circuit contribution, and transformer impedance interactions must align precisely with the host substation configuration. These are not issues that can be resolved late in the development process. When protection coordination challenges emerge during final design or commissioning, schedule impacts can quickly cascade into financial consequences. Fire code integration is another defining dimension of urban storage development. While national safety standards provide a baseline framework, authorities having jurisdiction commonly require project-specific hazard mitigation analysis. Equipment spacing, deflagration venting pathways, emergency access lanes, and first responder coordination must be integrated into conceptual design. Early and transparent engagement with fire officials not only improves compliance outcomes, but strengthens community confidence in high-visibility industrial areas. Construction sequencing in constrained sites further amplifies execution risk. Limited staging space, delivery timing, crane access windows, grounding system completion, communications integration, gas detection commissioning, and SCADA readiness must align precisely. Energization frequently depends on narrow utility outage windows. Integrated project management across civil, electrical, protection, and commissioning teams becomes indispensable to avoid compounding delays. Market value emerges from local grid constraints. From a market perspective, storage in load pockets can generate differentiated revenue characteristics. Congestion relief events, localized resource adequacy requirements, ancillary service participation, and nodal volatility may produce value streams that differ from remote installations. However, these opportunities require disciplined modeling. Urban development costs tend to be higher. Entitlement timelines can be longer. Interconnection upgrades demand careful negotiation. Historical nodal spread analysis, dispatch sensitivity modeling, and conservative revenue assumptions should inform investment decisions rather than short term price signals. Why corporate energy buyers should pay attention. For corporate energy buyers and sustainability leaders, the implications are increasingly material. Reliability risk is no longer abstract or evenly distributed. A portfolio level renewable procurement strategy may appear robust, while specific facilities remain exposed to congestion driven volatility or curtailment at constrained nodes. Storage strategically located within industrial corridors can provide resilience that extends beyond wholesale arbitrage. As electrification expands across transportation fleets, manufacturing processes, and high density computing infrastructure, the need for flexible capacity within concentrated demand zones will intensify. Urban grid edge storage is not a substitute for remote renewable generation. It is a complementary layer of infrastructure that strengthens system performance where demand and constraint intersect. As transmission expansion timelines lengthen and load growth accelerates, these load pockets will increasingly influence overall grid stability and economic outcomes. Developers and corporate stakeholders who recognize this structural shift toward localized reliability solutions and who integrate engineering rigor, fire compliance, interconnection precision, and disciplined financial modeling from the earliest stages will be best positioned to deliver durable, high-value infrastructure in the next phase of grid modernization. Arun Muthukrishnan is a senior development professional specializing in utility-scale solar and battery energy storage systems across U.S. organized power markets. He has contributed to the development of more than 1 gigawatts of renewable and storage assets, with experience spanning interconnection strategy, urban industrial siting, grid reliability integration, and complex permitting environments. His work focuses on aligning engineering rigor, market design, and disciplined financial modeling to deliver resilient infrastructure in transmission-constrained regions. Arun has published industry analysis in leading energy trade publications and has served as a judge for the Environment and Energy Leader Awards.